Hello, welcome to Scholar Fedu. This is our JAMB prep series where we provide relatively detailed solutions and explanations to the UTME questions. And in this recording, we are looking at the UTME questions for physics for the year 2014. This is the first part of the recording. We are going to look at the first 25 questions out of the 50 questions for this year. Before we continue, please don't forget to subscribe to our YouTube channel, like and share content. You can also visit our website at collab.com to practice the UTME exam for free. Alright, first question here is on the paper type that we have. Which question paper type of physics is given to you? So in this recording, we're using the paper type F. Okay, now this question is very important. Okay, it is important that you pick the paper type that corresponds to what you've been given. Alright, because that determines how your exam is going to be marked. So if you pick the wrong paper type, it can affect your results. So check out for the paper type that you have, okay, and make sure that you pick what corresponds to it in this sort of question. Next, on measurement, what is the least possible error encountered when taking measurement with a meter rule? That is 0.5 millimeter. That is the reading accuracy of a meter rule. A meter rule can be used to measure as small as 1 millimeter. Okay, its reading accuracy is half of its smallest reading. Okay, the smallest possible reading with it is 1 millimeter, so its reading accuracy is half of that. So half of 1 is 0.5 millimeter. That means that any measurement that is taken, or a measurement taken with a meter rule, can be written as, let us say that the measured value, okay, that is observed by the person using the meter rule is x. We can represent that measurement as x plus or minus is 0.5 millimeter. Let's say, for example, the measurement is 10. The person measured 10. All right. Now we can take that measurement to be within the range of 10 plus or minus 0.5. So if somebody reads that thing to be like 10.5, for example, that would still be correct. If somebody reads it to be 9.5, that's like 10 minus 0.5, that would still be correct. So anything within the range of 9.5 to 10.5 would still be a correct measurement for that length there. Okay, next question on quantities. A quantity which requires magnitude and direction to be specified is, alright, that quantity must be a vector quantity. Okay, vector quantities require magnitude and direction for that specification. And from the list, from these options that we have here, the vector quantity here is displacement. The others are scalar quantities. They require only magnitude, they do not require direction to be specified. Next, on quantity, unit and dimension. Which of these quantities listed are vectors? So like I said in the previous question, vectors quantity, they required magnitude and direction for their specification. So from the options that we have here, the quantities that are vectors are the torque, okay, the torque and momentum. Torque and momentum are vector quantities, while electric potential and kinetic energy are scalar quantities. Next, on motion, which type of motion do the wheels of a moving car undergo? Alright, so the wheels of a moving car, they undergo combined motion. Okay, and that is, for the moving car, it is translational and rotational motion. Rotational in that the tire rotates about a fixed point. Okay, it moves in a circle about a fixed point. And translational because in whatever direction that tire is facing, it moves in a straight line. Okay, in whatever direction it is facing. So the motion of the wheels of a moving car is rotational, okay, and translational. So you have rotational and translational. Next, we have a diagram here. From the diagram above, the region of zero acceleration is, now this is a velocity time graph. That's a graph of velocity against time. Now on this graph here, as we go up like this, the velocity is increasing. Okay, now the point on this graph where this graph slopes upward like this are the points where we have positive acceleration. That is, what this sloping upward means is that there is increase in velocity over time. Okay, so this region now, MN, is a region of positive acceleration, not zero acceleration. This region SP is also a region of positive acceleration. Okay, because this indicates an increase in the velocity with time. This region here, PQ is a point of negative acceleration, because this thing here, this graph here, is sloping downward at this point, meaning the velocity is reducing. Okay, is decreasing over time. But the point of zero acceleration is where there is no increase or decrease, and that is this point here. Okay, you can see that this point is just flat. This point, this region NX, is, you know, like parallel to this axis for time. Now you can see this region, there is no sloping upward or down. That means that there is no acceleration at this point. What we have at this point is what we call uniform velocity. It means that the velocity of that body was maintained over time at this point here. Okay, next question on motion, and these are some calculations here. A car accelerates uniformly from west at 3 meters per second square. Its velocity after traveling a distance of 24 meters is. Alright, since the car is coming from west here, its initial velocity u will be equal to is 0. Okay, and it says the question reads that it accelerates uniformly at 3 meters per second square. So this is the acceleration of the car. Okay, the distance that it covers is 24 meters. So we have to find its velocity after traveling that distance. That is what is its current velocity after it's moved this distance. Okay, so to do that, we are going to be using the third equation of motion. V squared is equal to u squared plus 2s, where this v is the velocity, like the final velocity. Okay, or we can say, relative to this question, this is like the velocity after it traveled 24 meters. This u here is the initial velocity. 2, of course, 2. A is acceleration of the car, and s is the distance that it moves. So we have v squared is equal to, our initial velocity is 0 because that body is initially at west. It is starting from west, meaning it has 0 velocity, plus 2 times the acceleration, which is 3, times the distance, which is 24. 2 times 3, that is 6, plus 24 is 144. Is 0 raised to power 2 is 0 times 0, that's just 0. 0 plus 144 is 144. So you have v squared is equal to 144. To get the value of v here, we take the square root of both sides. So when you take the square root of both sides, the square root of v squared is going to be v, and the square root of 144 is 12 meters per second. So this will be the velocity of that body after traveling, you know, a distance of 2 meters. Next question on gravitational field. Calculate the escape velocity of a satellite launched from the Earth's surface if the radius of the Earth is 6.4 times 10 to the power 6 meters. Alright, the formula for the escape velocity is given as v is equal to root 2gr. Okay, the square root of 2gr. That is 2 times g, which is 10. Okay, the escape velocity is given as root 2gr, where this r here is the radius of the Earth. So you have this as the square root of 2 times the value of g, which is 10, the association due to gravity, 10, approximately 10, times the radius of the Earth, that is 6.4 times 10 raised to power 6. Now when we multiply this, 2 times 10, 20 times 6.4, we are going to get 128. Now from the rule of third, if I have root a times b, I have a times b, both of them are under root, I can split that root between them. So I can write root a times b as root a times root b. So here we have root 128 times 10 raised to the power 6. We can write it as root 128 times root 10 raised to the power 6. Now the square root of 128 is what we have here, 11.3137 times 10 raised to the power 6 means 10 times 10 times 10, 10 like in 6 places, and that will be 1 million. The square root of 1 million is 1000. Okay, that's 10 raised to the power 3. Okay, so you say this is 11.3137 times 10 raised to the power 3, which is 1000 meter per second. Now 1000 meter makes 1 kilometer, right, as we sing in elementary. Okay, 1000 meter here is 1 kilometer. So we say this is 11.3137 times 1 kilometer. So this will be 11.3137 kilometer per second, and we can write this as approximately 11.3 kilometer per second. Okay, next question, also on gravitational field. An object of weight 80 Newton on Earth is taken to a planet where acceleration due to gravity is 1/3 its value on Earth. The weight of the object on the planet is. Now weight, okay, varies directly as acceleration due to gravity. Okay, now if the weight of the body originally is 80 and they now take that body to a place where it's where the acceleration of gravity, the acceleration due to gravity is 1/3 its value on Earth, that means that the weight of that body on that planet is going to also be 1/3 of its value on Earth. So the weight of the body on that planet is equal to 1/3, that's 1/3 times the weight on Earth. So you have 1/3 times 80. Okay, 1/3 times 80 is going to be 80/3. 80 divided by 3 is 27 Newton approximately. Next, on equilibrium and moment of forces. One of the conditions necessary for an object to be in equilibrium when acted upon by a number of parallel forces is that the vector sum of the forces is. The vector sum of the forces must be 0, okay, for the body to be in equilibrium. Next, also on equilibrium and moment of forces. What happens when three coplanar non-parallel forces are in equilibrium? Okay, their lines of action must meet at a point. Okay, their lines of action must meet at a point, must be convergent. We have a website at Collab.com where you could practice exams for free, the UTME exam and the post UTME exam. It also features modular quizzes in physics, chemistry and biology. So if you've studied a topic in any of the subjects and you want to test your understanding of the topic, you can head on to our website at Collab.com and take modular quizzes for free. Also, if you sign up on the website, it has a personalized dashboard where you could use to check your progress in learning. We also have interactive sessions on the website and on our social media platform. Freebies are also available to top performance on the website. Next, on work energy and power. An object of mass 20 kg is released from a height of 10 meters above the ground level. The kinetic energy of the body just before it hits the ground is. Alright, the kinetic energy of that body before it hits the ground is going to be equal to the potential energy of the body at that height, okay, above the ground from which it was released. So instead of using the half mv square, okay, which is okay the formula for kinetic energy, we would use the formula for potential energy. Okay, so we calculate the potential energy of the body at that height, and potential energy is given as mgh, mass of the body times acceleration due to gravity times the height. Okay, so you have this to be equal to the mass of the body from the question is 20 kg. The acceleration due to gravity is approximately 10 times the height above the ground at which the body was held, which is also 10. So you have 20 times 10 times 10, and that is 2000 joules. Next, on nuclear physics. The energy in the nucleus of atom produce heat, which can be used to generate. The heat can be used to generate electrical energy. Okay, it can be used to generate electrical energy. Alright, next on machine. A machine whose efficiency is 75% is used to lift a load of 1000 Newton. We have to calculate the effort put into the machine if the machine has a velocity ratio of 4. Alright, so the mechanical advantage of a machine is equal to the load of the machine over the effort. Okay, so this is supposed to be the formula that we're going to use. They are supposed to use directly to get the effort. However, in this question they only give us the load, they did not give us the mechanical advantage, so we need to look up for another way to get mechanical advantage, and that is by using the formula for efficiency. So the percentage efficiency is equal to mechanical advantage over velocity ratio. Now you can see that here I did not say mechanical advantage over velocity ratio times 100%. Why? Because there are many ways to do this, okay, and one is this that I'm doing here is that the value of your efficiency, okay, you can divide it directly by 100. That is the 100 that's supposed to be on this side. I can just use to divide whatever I'm given for efficiency. Okay, so if I do that, I don't need to add a times 100% on this side again, so I can just use this formula directly. So from here we now see that efficiency from the question is 75%. Alright, so I'll divide that by that 100, the 100 that's supposed to be here. So I'll just say 75 divided by 100, that is 0.75. Or you say express the 75% in decimal. Okay, that's another way to put it. Express it in decimal. So you have 75 divided by 100, and that is 0.75 is equal to the mechanical advantage over the velocity ratio of the machine, which is given as 4 here. Then for me, I'm going to cross multiply this 4, and so we have mechanical advantage to be equal to 0.75 times 4, and that is equal to 3. Now that we have our mechanical advantage and we have the load already from the question, that's 1000 Newton, we can then find our effort. So we say the mechanical advantage is equal to the load over effort, which is equal to 3. That is the mechanical advantage is equal to 3. The load here is 1000, so you have 1000 over the effort is equal to 3. We cross multiply. Okay, we cross multiply, so you are going to have 1000 to be equal to 3 times the effort here. Okay, so you have 3E. To get the value of the effort here, that's E, we divide both sides by 5. So you have E to be equal to 333.3 Newton. Next question, also on machines. A wheel and an axle is used to raise a load whose weight is 800 Newton when an effort of 250 Newton is applied. If the radius of the wheel and axle are 800 mm and 200 mm respectively, the efficiency of the machine is the efficiency of a machine is given as the mechanical advantage over the velocity ratio times 100%. Now the mechanical advantage is equal to the load over effort, and from this question here, the load is the weight of the load. Okay, that's 800 Newton divided by the effort, which is 250 Newton here. So you have the mechanical advantage here to be equal to 3.2. The velocity ratio for a system like this where we are having wheel and axle, the velocity ratio is equal to the radius of the wheel, which is 800 mm, divided by the radius of the axle, which is 200 mm. 800 divided by 200 will give us 4 here. So here now we have our mechanical advantage and our velocity ratio. We can then find our efficiency. So you see the efficiency is equal to mechanical advantage 3.2 divided by velocity ratio 4 multiplied by 100%. 3.2 divided by 4 would be 0.8. 0.8 times 100% would then be 80%. So the efficiency of this machine here is 80%. Next, on elasticity, a force of 500 Newton is applied to a steel wire of cross-sectional area 0.2 meter square. The tensile stress is the tensile stress is given as the force over the area, the cross-sectional area. The force here is 500, the cross-sectional area is 0.2. So you have the force 500 over 0.2. That will give us 2500 Newton. Alright, 2500 Newton per meter square. If you write this in standard form, 2500 is the same thing as 2.5 times 1000. Okay, 2.5 times 1000, and 1000 can be written in index form as 10 raised to power 3. Alright, this should be raised to power 3. It should be as a subscript, a superscript. Next, on elasticity, from the diagram above, the point that represents the elastic limit is the point Q. The point Q here is the elastic limit. The point R is the yield point. Okay, the point S is the maximum load, while T here is the breaking point. Okay, that's what we have here. Sometimes the points on this graph, on this load extension graph, can be like 5. In such a situation, the first point, okay, is usually the proportionality limit. Okay, the proportionality limit. The next one is going to be the elastic limit. Then we have the yield point, the maximum load, and finally the breaking point. Okay, but here, since we have just 4 points on this graph, we take this to be the elastic limit, then this as the yield point, this as the maximum load, and this as the breaking point. Next, a small droplet of water that forms on the grass in early hours of the morning is called dew. Okay, it's called morning dew. Alright, it is the small droplets of water that you will notice on the leaves. Okay, the leaves of plants in the early hours of the morning. What is the equivalent of 20 Kelvin in Celsius scale? Alright, to convert from Kelvin to Celsius scale, we subtract 273. If you want to convert from Celsius to Kelvin, you add 273. If you are converting from Kelvin to Celsius, you subtract 273. So if you want to convert this to Celsius, then we subtract 273 from it. So you are going to have 20 minus 273, and that is minus 253 degrees Celsius. Now if you have a past question and you cross-reference this question, you see that it is not exactly what you have there. So we think that there's a problem with the question, and so we decided to like edit it, put it in a way that makes more logical sense to us, okay, we should say. You can also join our online tutorial classes for different classes. We have tutorials for students in SS1, 2 or 3. We also have for UTME candidates, for JAMB candidates, for students who want to write the JAMB or the UTME exam, and for those who want to have the post-UTME exam after the UTME exam, and also for candidates that are sitting for WAEC exam or GCE or NECO. And we offer this tutorial on various platforms, so you could join us on WhatsApp or on Telegram, you could be on Zoom or on Google Classroom. So we have various platforms where we take our tutorial. The links to join the platform are available on our website at collab.com, or you could also check it out in the video description below. Next, on expansivity, a glass bottle of initial volume 2 times 10 raised to power 4 centimeter cube is heated from 20 degrees Celsius to 50 degrees Celsius. If the linear expansivity of glass is 9 times 10 raised to power minus 6 per Kelvin, the volume of the bottle at 50 degrees Celsius is. Alright, so the bottle was heated from 20 degrees Celsius to 50 degrees Celsius. The change in the temperature, that's the catheter here, of that bottle is going to be 50 minus this, that is the new temperature minus the old temperature. So you have 50 minus 20, and that is 30 degrees Celsius. The original volume of the bottle is 2 times 10 raised to power 4. Okay, 10 raised to power 4 is 10,000. That's 10 times 10 times 10 times 10. That's 10,000. 2 times 10,000, we have 20,000 cm cube. Okay, the volume expansivity is 3 times the linear expansivity. Why are we doing this? Because we are eventually going to come and use this formula here for volume expansivity, and in the question they did not give us the volume expansivity. What they give us is the linear expansivity, from which we can calculate the volume expansivity. So we calculate the volume expansivity first. So we say the volume expansivity is equal to 3 times the linear expansivity. So that will be 3 times the value of linear expansivity, that's 9 times 10 raised to power minus 6. 3 times 9 is 27, so you just have 27 times 10 raised to power minus 6 per Kelvin here. Now we have this formula here for volume expansivity, that the volume expansivity is equal to the change in the volume of the bottle divided by the original volume of the bottle times the change in temperature. We want to calculate the change in the volume here. Alright, the question is to calculate the new volume, but in order to calculate the new volume, we need to know what is the increase in the volume. Let's say, for example, if the original volume is 10, okay, and the change in the volume is 20, that means that I know that the new volume is going to be 10 plus that 20. Okay, so that will be 120. So what this point is that we need to first know what is the change in the volume first, okay, before we can calculate the new volume. So that's what we are trying to get from this formula here. So when you cross multiply this, we have the change in volume to be equal to the volume expansivity times the original volume times the change in temperature. So here we have the volume expansivity, which is calculated here, 27 times 10 raised to power minus 6 times the original volume, which is 2 times 10 raised to power 4 times the change in temperature, which is 30. By the time we multiply all of this, we are going to have 16.2. Okay, how do you multiply this? Just do 27 times 2 times 30 times 10,000 times 10,000. This 10 raised to power 4 is 10,000. Then divide it by 10 raised to power 6, which is 1 million. Okay, 10 raised to power 6. The reason why we are dividing is because this one is negative. This was a negative for power, so it will go to like the denominator. So divide by 1 million, you will get 16.2. Now that we know the change in the volume, to get the new volume, is just going to be the old volume, okay, the old volume plus that change in the volume. So you're going to have the old volume, which is 20,000 plus 16.2, and this will be 20,000 16.2 centimeter cube. Next question on gas laws. So you have this equation here: PA, pressure with P raised to power A, V raised to power B, T raised to power C is equal to constant. They say reduces to Charles law if, that is, this here is going to be a representation of Charles law if, that is, in what case, what will be the values of this A, B and C. Alright, so we know from Charles law that what, the volume is inversely proportional to temperature. Okay, from Charles law, volume is inversely proportional to temperature. If you write that as an equation, we are going to be having V proportional to T. Okay, then we have V is, if you turn that into an next on heat, the quantity of heat needed to raise the temperature of a body by 1 Kelvin is the body's, this defines the heat capacity of the body. The heat capacity is the quantity of heat required to raise the temperature of the body by 1 Kelvin. This should not be confused with specific heat capacity. Okay, the specific heat capacity is the quantity of heat needed to raise the temperature of a unit mass of a body. Okay, the temperature of a unit mass of a body by 1 Kelvin, and you can see that is omitted here. So that is, this is not specific heat capacity, this is heat capacity. Okay, so defining heat capacity, it is devoid of that unit mass. All right, so this defines heat capacity, not specific heat capacity. There are some questions where JAMB question, of course, where there has been temperature of a unit mass of a body and all of that. That would be specific heat capacity. Next, the melting point of a substance is equivalent to its the same thing as its freezing point or its solidification temperature. Okay, so the melting of a substance is also, like, the melting point of a substance is also called its freezing point. Even though melting and freezing, they are two contrasting processes, meaning that they are opposite processes. So melting is turning from solid to liquid, while freezing is going from liquid to solid. So what is happening there is, you can think of this freezing point or melting point as like somebody who is standing in the doorway. Okay, so the person who is standing in the doorway can either go out or go in, so depending on what direction that person is moving in. So at the melting point, if the temperature of the body continues to increase, that means that the body is melting, the body will be melting. But at the melting point, also known as the freezing point, if the temperature of the body continues to decrease, it means that that body is turning into a solid, this is freezing. Okay, so think of it as a two-way thing. All right. Next, the temperature at which water vapor present in the air is just sufficient to saturate the air is, this is the definition of dew point. Okay, the temperature at which the water vapor present in the air or the atmosphere is just sufficient to saturate it. That defines dew point. Next on heat transfer by convection in a liquid is due to the, so there are three methods of heat transfer. Okay, it could be by conduction, it could be by convection, or it could be by radiation. So by radiation is between two bodies that are not in contact. Okay, between two bodies that are not in contact, that is radiation. Like the transfer of heat from the sun to, the heat reaching us from the sun is by radiation. All right, because we are not in contact with the sun, with the heat source. Okay, that is radiation. By conduction is between two bodies that are in contact. However, this has more to do with solids. Okay, but with liquid it is by convection. And the heat transfer is due to the expansion of the heat as it is of the liquid rather as it is heated. So as that liquid is heated, it begins to expand gradually. Okay, liquids and solids generally, they expand when they are heated. So as it is expand, what is happening is that molecules, the heated molecules, are going to be traveling, and they will be moving towards, or they will be mingling, kind of moving between the colder molecules, transferring heat to them, and that way, okay, the heat is gradually transferred, okay, by convection. Okay, don't forget to check out our playlist. We have different playlists. We have for full solutions to UTME or JAMB questions and in physics, chemistry, and biology. We also have for modular quizzes as well. Okay, we'll also have a playlist for post UTME or post JAMB exam, and also for crash courses in physics, chemistry, and biology. So don't forget to check out our playlist for the available videos. So that's it for this recording. Thank you very much for watching. Please don't forget to subscribe to our YouTube channel at Collab. Okay, like and share our content, and visit our website at collab.com to practice UTM exam and modular quizzes for free. Thank you.